Right, indeed. So today is the final lecture in my lecture series. And I thought, so my plan for today is I will continue a little bit the story from last time. So I'll finish up some of these strange constructions that we started making related to the Knop-Co cycle to try and show you some of the invariants, the arithmetic invariants that are in the title of my lecture series, essentially. And then I would like to shift gears and go more towards trying to illustrate what I think could be some aspects of a purported p-adic Kudla program. But I would like to be very clear in saying, my title has a question mark at the end. I don't know the way. I'm not here to tell you what the p-adic Kudla program is. Rather, my goal is a bit less ambitious. It's to give you a couple of data points of things that I think might fit such a Kudla program, and then leave the question to you to try and think along to see sort of what the outline of such a program might look like going forward. Okay, so that's my goal for today. So through the lens of a couple of very particular instances, and I will focus, there's many by now, so there's more and more in the literature, but I will focus on two, the two that mirror the closest the work of Gross and Zagier that we spent some time trying to digest in the previous couple of lectures. So those are the ones that I will focus on, but by no means are they the only ones that appear in the literature, so that should be clear. Okay. All right, so first, since it's been 2 days since the previous lecture, let me just quickly recap some of the salient big picture points of the work of Gross and Zagier that I would like you to keep in the back of your mind for when we move to the RM setup. Yeah, so in the first part, in CM singular moduli, it's just a recap. There's nothing really new that I would like to tell you. So I read a little bit of this recollections of Dick Gross, of this collaboration, which was about a certain week in 1982. This is a letter which is also public, and it's great fun to read these things. It's from 1983. It's a letter from Zagier to Dick Gross. The whole letter is available online, and it's been transcribed as well. And it's where essentially he describes the analytic proof which I'd like to put center stage today in our explorations of the p-adic Kudla program. So Zagier, you can see already, very familiar by now. I've slapped you around the head with lots of explicit examples, but I'm just imitating Zagier in a sense. So he really did lots of calculations, lots of numerical experiments to lead him to the discovery that there's actually a very beautiful formula for the difference of two arbitrary singular moduli, whereas the previous anecdote had focused more on individual J invariants and J minus 1728. This is the letter where Zagier sort of explains that many of these observations carry over in full generality for any pair of CM discriminants. So one of the examples you see in this letter is the difference of these two J invariants, which I factored for you, so they're both highly factorizable. But so is their difference. So their difference also, it's a very large number, but it has a very, very smooth factorization, so only very small prime factors relative to the size of this humongous integer appear. Okay, so there's an exact description of this factorization, but let me just point out a couple of qualitative things about it, which we already mentioned plenty of times before. So all the primes that appear in this factorization, so 3, 5, 7, 13, 17, all the way up to 283, they all share the property that they're non-split in both of the imaginary quadratic fields that define these invariants. Yeah? So with respect to minus 7 and minus 63, they are never split. They're always inert or maybe ramified. But more precisely than that, a little bit further in the letter, Zagier tabulates the prime factorizations of positive integers nx, which are, it's a finite set of integers that are of the form 7 times 163 minus x squared divided by 4. Yeah. And the positivity here, of course, makes that into a finite set of integers. You can write down that finite set of integers and you can factorize it. So these are all the values of x that give you something of this form. And then you look at the factorizations and you notice that all of the prime factors that appear up there, oh, this works, that's great. Up here, ooh, this is a little bit funky to work actually. Okay, these ones all appear once in here, and in some sense the explicit formula tells you exactly how many times it appears. So the formula I had on the board in the first lecture tells you exactly the exponent really of these primes in the factorization. Okay, so that's a little bit what we saw before. Right, and then we dug a little bit into how the proofs go, and we discussed two different ways to approach the proof, which is what you find in Gross and Zagier's first paper on singular moduli. So recall that Zagier had, in his letter here that I mentioned on the previous page, he sketches this proof, this analytic proof. So he makes this explicit formula for the ORD Q of the norm of the difference of two singular moduli as a sort of character sum, and then he proves this explicit formula using this real analytic Eisenstein family of Hecke that we had on the board in the last lecture. So it depended on a parameter S, which is a real parameter greater than 0, and the behavior as S goes to 0 was what interested Zagier in this letter. So it's a Hilbert modular form over Q square root of delta 1 delta 2 of weight 1 1. Full level 1, but it's not holomorphic. It's real analytic for a general parameter S. Okay. So one remark that's important going forward is to note that in the proof, in this letter, Zagier doesn't use CM theory at all. So he doesn't really use the algebraic nature of J tau 1 and J tau 2. It sort of comes along for the ride. He doesn't have to really prove it, and he gets the factorization at the end of the day without really relying on CM theory, which is a significant fact for us later on. So at the end of the letter, he challenges Gross to find an algebraic proof, and the letter that comes back the other way is also available. And you can see there that Gross takes very much this point of view that we took last time. So just to recall, so he figures out what the ORD Q is of this norm of the difference of singular moduli by studying really embeddings of the rings of integers of these two imaginary quadratic fields into orders in the quaternion algebra ramified at infinity and Q. That's a little bit the viewpoint we took last time, and we even worked out a very specific statement in detail. So in the end, this is the shape of his formula. So he says the ORD Q of this quantity, this norm, is the sum over all of these possible pairs of embeddings, where you conjugate one and you intersect it with the other, and then times some multiplicity where the multiplicity measures how congruent the images of these two rings are modulo powers of Q. Yeah? So that's a little bit, just big picture, the shape of the two proofs that I want you to recall as we go forward. Okay, any questions before we move back to the real quadratic setting? So I realize I have slides, which is not always easy to follow, so I apologize for that, but don't worry. So you can see I only have 20 slides, and 5 of them are title slides. And we just had the recap slide, so I intend to go very slowly, so feel free to Sorry? Yes, absolutely. In the return letter that he sent back to Zagier contained the algebraic proof, which is based exactly on these methods of counting embeddings into quaternion algebras like we did before. Yeah. And then, of course, in the paper, they work out both arguments, and both, in the first paper, give you an alternative proof of the same thing. But as we know, in the subsequent Gross-Zagier work, where they really compute the heights or the height pairings of Heegner points, both become independent ingredients or independent contributions to the global height, which is not necessarily 0 as soon as you leave the full level structure x of 1 modular curve. So they both have an essential role to play. Okay. All right, so let's then go back to the RM setup. And last time I started telling you sort of a strange story with these cocycles that were valued in sets of rational functions on C, so on P1 of C. That were defined by Marvin Knopp in the late 70s. And so I would just like to finish off that story and really bring it to a place where you can at least appreciate why we would write down such objects, which is a little bit mysterious perhaps at this stage. So again, recap. So last time we defined this Knopp cocycle, and it was associated to a quadratic form f of some positive discriminant delta. The discriminant was allowed to be a square if it wanted. And this is roughly the shape of, well, this is exactly maybe the shape of the cocycle that we defined last time. So what we did is we chose a base point B in the upper half plane somewhere, and we chose it generically. So we chose it in this set that we called XF, which was just a complement of the SL2Z orbits of all the geodesics that we get by looking at equivalent forms Q to the form F that serves as the input. Yeah? So for a generic base point B, we defined the following map. So it was a map from SL2Z to C of Z, rational functions, that sends a matrix gamma to the sum over all of the forms equivalent under SL2Z to F, so it's infinitely many forms, of this quantity, which is the sign of the form Q, B comma gamma B, multiplied by L of RQ, and L of RQ, I remind you, is roughly 1 over Z minus RQ. Yeah? It's just that if you have square discriminant, you have to be a little bit careful about the normalization, but that's what that is. So it's this L of RQ is a very simple rational function, and then you put it together into this sum using the sign, and the sign was defined for any pair of points x and y that are generic to be the sign of intersection between the geodesic going from x to y and the geodesic connecting the two roots of the quadratic form, where RQ was defined as this canonical root, the first root where you choose the plus sign in the quadratic formula, essentially. Yeah?
Yeah.
Yes?
Could you maybe just on the sideboard recall what RQ and LRQ is?
Absolutely, yeah, that's a good idea. So recall, so if Q is a form A, B, C, then RQ is this number. It's what we call the first root of the quadratic form, and because delta is a positive discriminant, this is a real number. Yeah, so it's somewhere on the real line here. Let's say. RQ prime, that's the other one where I choose the minus sign instead of the plus sign. Yeah? And then, well, since I've written it here anyways in this non-homogeneous form, I might as well also take this more simple-minded definition. So it's 1 over Z minus RQ, where Z is the variable on P1. So it's a simple rational function that has a pole with residue 0 at this real quadratic singularity RQ. Okay. Yes?
Can the base point be anywhere, or does it have to be in the boundary?
Yeah, I didn't say that here, but so the base point B has to be generic. Maybe I should have put that on the slide, in the sense that it can be anywhere in the upper half plane, even extended upper half plane, as long as it's not on any of the translates of this geodesic. So RQ, when you work on it, when you act on it by SL2Z, there's lots of geodesics that appear in this sum, and the base point B should not be on any of them, which is possible because all these geodesics have measure 0 together. So as long as you stay away from any awkward choices of B, you're good to go. Yeah? So in the situation where delta is not a square, you can choose B to just be the point at infinity, if you like. And that's usually the convenient choice to make whenever we're dealing with a non-split form. But since I like to include split forms today for the second part of the talk, I don't insist that B is infinity, because that would be a bad choice. Okay, any other questions about this definition from last time? Okay, so I gave the sort of homework or exercise, which I know some of you have done, is to check that this sum here on the right-hand side is a finite sum, which of course it better be if this is going to be a rational function. Of course, if this is an infinite sum, this wouldn't make sense. But the first thing to check is the finite sum. So it defines for me a rational function. And the set of all of these rational functions, which depend on gamma, is in fact a cocycle. It's a cocycle for SL2Z valued in C of Z. And that's what the Knop cocycle is. Okay? All right, so the plan today is to do exactly the same, but we're going to enrich this situation by replacing the group SL2Z, acting on the module of rational functions CZ, by this much bigger group, which is SL2Z1 over P, the Ihara group, so where I allow my entries of my matrices to have denominators at P, acting on M, where M will be the module of meromorphic functions on the p-adic upper half plane HP. That's the plan for today. Now, if you've understood the Knop cocycle, the jump is not that big anymore, so all the weirdness is already present in the rational cocycle one, so the exercise from yesterday is still a very relevant one. But then I will tell you, hopefully, convince you, why we made this definition. So I will use these enriched cocycles to produce RM invariants, so numbers that appear to be interesting in a way that I will specify with lots of examples. Okay, so that's the plan. Okay, so first the p-adic upper half plane, or the p-adic half plane is perhaps a better name. So I'll consider the projective line P1. So P1 is a beautiful algebraic variety, and I can define these aphanoid subsets HP brackets n by the condition that whenever you take, so you take all of the projective points, which I'll denote here by Z1, Z2, again with the same column notation, so up to scaling, but I'll take them to be primitive, so I'll take them to be both integral and have no common divisor, so one of them has valuation 0. Okay, so then the condition is that for any pair of primitive integers r and s that I take in z squared, the absolute value of s times z1 plus r times z2, in the p-adic sense, is at least p to the minus n. So this defines for me an aphanoid subset of P1CP, which is roughly the complement of disks of size p to the minus n around all the rational points. That's another way of saying this, which is a finite collection for any given n. But now what I'm going to do is I'm going to put these all together, and I'm going to consider the limit, so this is a direct limit of all these HPNs, and that's what we call HP. And maybe the most concrete way of thinking about HP is, it's a rigid analytic variety, but on the level of CP points, it's just P1 of CP, where I take away the QP rational points. So that's what this HP will be. Okay. Now, usually there's a sort of convenient combinatorial tool that we will maybe use a couple of times today in our explorations, which is the Brouhat-Titz tree. And it gives you a way to think of this p-adic upper half plane, or the p-adic half plane, I should say, by comparing it with this object, which is really, as a combinatorial object, a very simple thing. It's a graph that's p plus 1 regular. And that's what the Brouhat-Titz tree is. And so there's a natural reduction map from this space HP to the Brouhat-Titz tree, which often allows you to give sort of nice estimates on HP. It's a tool that you frequently use in estimates, and it makes it maybe more visually appealing. This reduction map, what it does is it takes HP 0, so the smallest of all of my aphanoids inside of P1 that I've taken, and it sends it to a distinguished vertex. Let's say it's the one in the middle here on the picture. The aphanoid HPN will then be sort of the inverse image of the reduction map of all of the vertices of distance at most n to v0. And so a good way to visualize the p-adic half plane, if you haven't seen it, is as a tubular neighborhood of this graph. So around every edge, you should sort of imagine a tube. It's not on the picture, but it's sort of a tube that goes around all of these edges and branches out infinitely as this graph branches out infinitely. It gives you sort of a convenient way to keep track of where you are in the upper half plane. Anyway, we won't use it much. But what I want to say is that this HP, this p-adic half plane, now gives us our enrichment of the rational functions that we were looking at by allowing us to consider certain limits of rational functions as functions on this space. And so the functions that we'll be interested in is the set of meromorphic functions on HP, which I'll define to be the set of uniform limits with respect to all of the supremum norms on all of these aphanoids inside of HP of things that are just rational functions. So I'll consider the space of functions which, when you restrict them to any HPN, it's just a uniform limit of rational functions. So it's sort of the minimal amount of notion that I need to be able to make sense of p-adic limits of these Knop cocycles. That's really the space that I want to put myself in. Okay? All right, and that's exactly what will happen in the next definition. So the Knop cocycle was a very explicit thing, and I'll keep that very explicit definition, and the convergence will now happen inside of this particular module, which is a module for SL2Z1 over P with the same action, weight 2 action that we considered before. Okay. So that's what I'll call M. All right. So why not imitate the recipe of Knop and tweak it in two crucial ways? And I'll say at the end what these two crucial ways are. So as before, we'll put ourselves in a situation where we have a quadratic form f with discriminant delta greater than 0. So we can already make sense of the Knop co-cycles. And I will also choose a base point b in xf, where this xf is the same xf I described before, but now I don't want to be in any of the translates of any of these geodesics for the group SL2 Z1 over P. Okay, so I take a generic B again. All right, so now what do? I essentially take the same expressions as before, but I switch the group from SL2Z to this group, which I'll call gamma henceforth, SL2 Z1 over P. Okay, so here it is. There's two cases. Depending on the splitting behavior of P in the algebra spanned by F. So if P is non-split, like for instance, F defines some real quadratic field and P is inert in it, that's the typical case that we will care about, then I define the following map. I'll call it theta F star. And theta F star is going to eat a matrix gamma in my group big gamma, and it's going to send it to this infinite product, which runs over a set very similar to what we saw before for the Knop co-cycles. It runs over all of the quadratic forms Q, which are equivalent to my input form F under this group gamma for the usual action of matrices on quadratic forms. So it's a huge infinite product. It's indexed by the elements of gamma. And for each quadratic form that I get by acting with my element little gamma on, with my element of big gamma on F, I get Z minus RQ, yeah, so essentially this L RQ inverse raised to the power the sign of intersection precisely as defined before. Okay? All right. This non-split condition, it's not that crucial. When P is split, you can also make a definition, but for technical reasons, for convergence reasons, you have to include one other factor. You have to take these quotients of Z minus RQ divided by Z minus RQ prime to make it convergent. So it's not super important, but essentially the same formula, regardless of the splitting behavior. Okay. Now, of course, something needs to be checked. What was true before is that the sums that we saw in the Knop co-cycle were really secretly finite sums. So finitely many terms gave you a non-trivial contribution to that sum. Here, this is no longer true. So this product, it's really an infinite product, even though this sign condition in the exponent will eliminate a lot of the terms. They will still leave infinitely many terms in this infinite product, and so the first thing you have to worry about is whether this infinite product really does converge. And that's the first claim. The infinite products converge, and they converge to meromorphic functions on HP. And you can now sort of see how you might prove that. You have to estimate, with respect to the supremum norm, what these products look like, and you will see that it converges essentially by definition of my set of meromorphic functions. Yes? Yeah.
And I get something that looks like the Knop co-cycle, but with L, which is replaced by log.
Yes, well, you would essentially have log of L, yeah, because the 1 over doesn't really do anything, it changes the sign, yeah. Yeah, absolutely, you could do that. In fact, sorry.
Yeah, no, maybe this raises the question whether the Knop co-cycle with L replaced by log L is also a co-cycle.
Yeah, so I'll get to that actually, because you've put your finger on, I think, the second change that I haven't really discussed. I put a lot of emphasis that we changed SL2Z to gamma, but indeed, as you point out, we've done another very crucial change. We've changed all the sums to products. Yeah. So the co-cycle was previously additive and is now multiplicative. In fact, if you apply the logarithmic derivative to this one, you get an additive version of the Knop co-cycle. So we've enriched it in two ways. We've enriched it by enriching the group, but we've also enriched it by identifying these pre-images for the logarithmic differentiation of what you would normally get from Knop's construction. So the construction you mentioned is extremely important. And that's the refinement that allows us to produce invariants that have algebraic behavior. Now, there's one other very important thing about these co-cycles. I said they're co-cycles, but I didn't say valued in what. Because of this business of changing from additive to multiplicative, so lifting for the logarithmic differentiation map, there is actually an error to the co-cycle condition as you would normally apply it in M star, the set of multiplicative meromorphic functions. And that error is always a constant. So it's very similar to the theta functions you see in the uniformization theory of Cherednik and Drinfeld. So if you check the co-cycle condition for the functions that I wrote down there, so the cross homomorphism identity, you express that, it'll be true up to a multiplicative constant. And that multiplicative constant is not necessarily equal to 1. So there's non-trivial periods that appear. So I have to change my module here to make it really into a co-cycle to M star modulo Cp star. Okay? Right, and then finally, just like in the case of the NOP co-cycles, the cohomology class that we get from this co-cycle is independent of the choice of base point. Yeah? So it doesn't really interfere. Okay, right, so two things happened, just to reiterate the obvious. We switched from SL2Z to gamma, and we switched from additive to multiplicative. Yeah? So those two enrichments will be crucial for what I'll say next. All right, now I haven't told you the most important thing yet, which is why should we care about this strange object? So let me try and convince you that these might be interesting to study. And here's the crucial thing. If you have one of these co-cycles, which henceforth I will call theta co-cycles, because they have this behavior of, they satisfy the co-cycle condition up to a multiplicative constant, just like p-adic theta functions would satisfy invariance up to a multiplicative constant. That's the justification for the name. They can be evaluated in a meaningful way. And so here, you have to pay attention to the subscript. So the theta co-cycle depends on the input of one quadratic form f. And the evaluation will depend on another choice of a quadratic form, which I'll call g. So the construction, really, the invariant, will depend on two pieces of input which play, ostensibly, a very different role from each other. So I'll define the evaluation only at g's for which p is non-split. That means if I have g, which I've called on the board here q, that this rq, or rg, the root of this quadratic polynomial, it's a global number. I can consider it in the Archimedean realization, it was on the real line, or I can consider it in the p-adic realization, so on P1CP. The condition that it's non-split means precisely that the root lies in HP, in the p-adic half-plane. Okay? All right, so suppose I give myself these two pieces of input, f and g. What do I do with these co-cycles? I do the following. So it's a little bit subtle. It's a little bit strange looking. The first thing you have to do is you take this theta co-cycle, theta f star, and it's a co-cycle up to constants. But this up to constants we can get rid of by doing the following sneaky trick. I will take this co-cycle and I will restrict it to a subgroup isomorphic to SL2Z. Yeah? SL2Z1 over P has many such subgroups, has these simple SL2Zs, and I will take a copy of SL2Z that contains the stabilizer of my form G in this big group gamma. Okay, so the stabilizer of G in this big group gamma, it's still an infinite cyclic group just as it would be for SL2Z, and I will restrict my co-cycle to such a subgroup containing the stabilizer. And then, why do I do that? Because this restriction is going to lift to a co-cycle which is valued in M star and not just in M star modulo Cp star. So I get rid of this ambiguity of a multiplicative constant. And the reason is the following, because once I restrict to SL2Z, the group gamma becomes a much simpler one. SL2Z has a much simpler cohomology. The classes, the theta co-cycles that I get by restricting theta f star to SL2Z, they live in the middle here. And there's an obstruction to lifting them to classes valued in M star, which is the H2 of SL2Z with values in Cp star. And that H2 is trivial for the group SL2Z. So there's no obstruction to lifting it. And you can lift it also in essentially a unique way because the H1 of SL2Z with values in CP star, it's very small. It's of size 12 essentially. So up to a 12th power, you get a well-defined, unique such lift, and that's the lift that I'll take. So you can eliminate, by sort of purely abstract formal reasons, the scalar ambiguity in the transformation law, but what you lose is maybe a very explicit description of what this lift looks like. So I had a completely explicit formula a couple slides ago. For this lift, it's a little bit harder to say what this thing is. It's the same formula up to some constant, but that's a constant that maybe is not so easy to write down. Yeah? Trivial. That's the trivial action. Yes. Yeah. Okay. Now, I have my lift. Bear with me, we're almost there. I take this theta f star, I restrict to SL2Z, and I lift. And now I take this lift, and it's a cocycle, so it eats matrices and it spits out functions, meromorphic functions on the upper half plane. So if it eats matrices, I better feed it a matrix, and that's exactly what I'll do, is I'll feed it the generator of the stabilizer in gamma of G. So there's a generator, there's even a distinguished one. If you have a form G, there's a canonical gamma G that generates its stabilizer. It's infinite cyclic, and that's the gamma G that I will feed into the restriction of my cocycle. Once I've done that, I have a function, and that function I evaluate at the root of G. Okay? So there's two evaluations happening. First, I evaluate the cocycle to get a function, and then I evaluate the function to get a number. Yeah? Those are the two steps that we've gone through. All right, so a lot of abstract nonsense, very strange looking definition. So the burden is now on me to convince you that this makes sense. Yes, question?
Do you have a convention for choosing the orientation so that you know which one to choose as generator, like gamma G or inverse?
Yes, absolutely. So gamma G, I said there's a canonical choice. That's because I've also made a canonical choice of my roots. And so my roots here, I have minus b plus the square root of d over 2a. There's another one, RQ prime, and any stabilizer here, gamma G, will fix both. It'll have two of these fixed points, but one will be stable and one will be unstable. So one will be an attractor and the other will be a repellent. And I choose the generator for which the RQ is the attractor point. You can also write down an explicit formula for it in terms of the Pell's equation if you like. But, yeah.
What is H2 gamma CP star? Is that not zero?
Sorry?
So why do we restrict it to Z? Is H2 gamma?
Yeah, H2 gamma. Yeah, it's a good question. Why did I restrict to SL2Z? It's precisely to make that lifting obstruction vanish. If I had not done that, it would be H2 gamma CP star, and H2 gamma CP star is not trivial. It's isomorphic more or less to H1 gamma 0 of PZ, so the space of weight 2 modular forms and level gamma 0 of P. And this will be important in what follows. Yes, so good question. So the restriction to SL2Z is there precisely to kill the lifting obstruction. Of course, yeah.
So can you describe this cocycle which you restrict to SL2Z and with values in M star?
Explicitly.
Yes.
So what it is, let me maybe go back to the previous slide, is it's the same expression that you see there times some mystery constant that depends on gamma. And the mystery is precisely what the set of constant is that applies to gamma. And I didn't make that explicit here in the slide. So I'm just saying there exists such a collection of constants, and I put those in, and those I will use in the evaluation. Yeah. Yeah.
But so what's the point of working with SL2Z1 over P instead of directly with SL2Z?
Because if you do the construction with SL2Z, those products would be finite products. And this evaluation procedure, it only involves numbers in these two quadratic fields. And if it's a finite product of such expressions, you will remain in the biquadratic field. So by changing from SL2Z to SL2Z1 over P, at least you give a chance to have an infinite product that is allowed to converge to a global number outside of this biquadratic field. That's a little bit the idea. Yeah. Okay. All right, so one thing that's perhaps a little bit surprising is that in my weird construction of this evaluation, the forms f and g play a completely different role. Now, one is used as the input for the definition of this strange knot cocycle. The other is used in this weird evaluation procedure, and they seemingly have completely different roles in the construction of this invariant. Now, in our first paper with Darmon, we checked that there is a kind of an anti-symmetry behavior in these invariants, but we check only a weaker version of this. And so very recently, Spreer proved that on the nose, the invariant that I've just defined doesn't really distinguish between f and g. It only distinguishes between f and g if you swap them around up to a multiplicative inverse. So the invariant that we just defined, as asymmetric as it looks, well, asymmetric is maybe not the word because it's anti-symmetric, so it isn't symmetric, but at least it has a sort of well-behaved symmetry. It's anti-symmetric in the multiplicative sense, on the nose. Yeah? So Spreer proves this using a sort of a more grown-up version of the cocycles than the simple-minded version I'm telling you now. And I think he's speaking next week maybe about this. I'm not sure, but he'll be here next week. So that's already a strange thing. But perhaps in and of itself, not enough to convince you that we should care about these weird numbers. So I've defined these numbers, theta p star fg. There's some p-adic numbers, but they're very explicit. So let's try and compute some examples. And this, I think, is the first example we ever computed. So there's a choice of a prime, and I'll choose the prime p equal to 2. Question?
Yeah, sorry, so when you restrict that to PZ, SN2G is always the same thing for each SN2G?
Say again?
SN2Z is just SN2Z or it's a copy of SN2Z?
It's a copy of SL2Z, yeah. Usually you will, usually you try not to be masochistic and take f and g to have sort of discriminants co-prime to p, in which case you can just use the standard copy of SL2Z in SL2Z1 over p. But if you try and make your life complicated by taking a G with a high conductor at P or something, then you have to take a conjugate copy. Okay. All right, so the example P is equal to 2. That's one piece of the input. Yeah, we have the invariant here. There's 3 things that I have to specify. There's a prime, there's an F, and there's a G. And out comes a number. Yeah? All right, so my prime is 2. The forms that I'll take are the following 2 forms. So I'll take 1 minus 1 minus 1, which has discriminant 5. Yeah, it's sort of the roots are the golden ratio. It's these real numbers. And then for my second form, I'll take 2 different ones, and I'll compute both of them. So I'll take 1, 3, minus 3. I'll compute the invariant, and then I'll also take minus 1, 3, 3. Both of these have discriminant 21, and discriminant 21 has narrow class number 2, and these are the 2 representatives for those 2 classes. Okay? All right, so this data gives for me 2 invariants. You compute this infinite product in some way that allows you to compute 300 coefficients. And what you do is you have this huge p-adic number, and then you use LLL, and you find that it looks two-adically extremely close to a root of this very small polynomial. And this polynomial here, there's a couple of things I would like to point out about it. It has very small coefficients. Yeah? And the first thing is maybe that its splitting field is the biquadratic field q square root of minus 3 and square root of minus 35. Yeah? So 2 imaginary quadratic fields. So even though the input of our invariant laid in these 2 real quadratic fields, the output sees also some imaginary numbers. So lives really not in the base field in some extension of it. Okay. So to point out the obvious, it's an algebraic number. It looks like an algebraic number very, very convincingly, which made us very optimistic that we should compute more examples and see what was going on with these kinds of invariants. Yeah? This kind of thing you don't find by accident. Another thing to point out is that this field, it's not some random field. If I take my 2 discriminants, delta 1 and delta 2, they're 2 real quadratic fields. They each have a Hilbert class field. Delta 1 with discriminant 5 doesn't have a very exciting Hilbert class field because that's class number 1. So the Hilbert class field is just q joined square root of 5 itself. Now H2, that comes from a discriminant with narrow class number 2. So the narrow Hilbert class field is a genuine quadratic extension of this real quadratic field q joined square root of 21, and it's precisely this biquadratic extension. Okay? And so we see that the roots that we found for this polynomial lie in the compositum of these 2 narrow Hilbert class fields.
Let me ask you a question.
Yeah.
So when you compute this theta 2 star, so how did you
Oh, you just computed
Yeah, I've swept a lot of stuff under the rug here. You're absolutely right. There's a trick here. So you can you sort of interpret this as modular symbols. And there's a trick where you can compute just with the expressions that I had on the board before in a way that makes the mystery constants cancel out. Yeah. And there's also lots of other tricks. I mean, if you do this naively, this infinite product has exponential growth in the number of terms. So that's not the way you want to compute it. This modular symbols interpretation as well leads to sort of much faster algorithms in the style of maybe, how should I say, Matt Greenberg, or I don't really know. Stevens, exactly. Stevens-Greenberg, yeah, indeed. So for overconvergent modular symbols, they use very similar tricks to get polynomial time algorithms in the p-adic precision. And that's also necessary here in order to get 300 digits of precision. But I haven't really mentioned any of the numerical hiccups, but there's plenty of them.
But you also said that the lift is well defined up to roots of unity, right?
Yeah, that's true. Or alternatively, because we know that those roots of unity are always 12th roots of unity, we just raise to the 12th power, and that ambiguity goes away. Okay. Yeah. But indeed, yeah. Yeah.
So these are the 4 roots of this polynomial because these are the inverses?
Yeah, it's a good question. So we'll get to this. Yeah, indeed, absolutely. That's exactly right. So there's some missing, though. So I've told you about 2 of the roots, because I've computed 2 invariants. Yeah? So there's 2 of the roots here, actually, that are accounted for, but there's still 2 missing. And I haven't told you where those roots come from. No, not quite. So they come from another quadratic form. So you have to also compute with a form f that has discriminant 5 times 2 squared. So there's a higher level. And that will account, so I didn't compute this one here. In fact, our algorithms don't really see anything that's not in the standard aphanoid. But that should account for the 2 missing roots in this picture. In fact, no, sorry, maybe we did compute it, actually. So I'm sorry. I didn't do justice to the algorithm. So all 4 roots can be constructed. And in fact, I'll tell you about, so right now we're just doing the first experiment. I'll tell you many more, and then I'll tell you what the general conjecture is.
But if you swap f and g,
You
you get the inverse.
get the inverse.
Aren't those the other 2?
Yes, you can do that also, yeah, if you want. Yeah. Okay. Right, so let's do another example. So we did the prime 2, let's do the prime 3. Let me take these 2 quadratic forms, very similar procedure. So we have discriminant 5 and 44. 44 also has class number 2. And then we find, again, some numerical invariant, and it appears to be the root of this degree 8 polynomial. Okay. So still similar considerations on the field of rationality, but what I'd like to focus on now is the factorization of these integers that appear in the coefficients. So the constant coefficient is 48,841, which, as you no doubt know, is 13 squared times 17 squared. So it's a big number, but it has small factorization. And qualitatively, we can say a little bit more about that factorization. For instance, the thing you can note is that both 13 and 17 are inert in both of these real quadratic fields. So already the situation is quite similar to what we saw in the work of Gross and Zagier. So let's imitate Zagier further and tabulate the positive integers of the form delta 1, delta 2 minus x squared divided by 4. And here it is, so it's a finite collection again. And we see, at least qualitatively, a similar thing appearing. The 13 appears here, and the 17 appears here. There's other things that appear, but let's get back to that later. So at least the primes that we see also appear in this table. So now we can dream that there's a formula for the factorization, very similar to the formula that Gross and Zagier had, except now in the setup of real quadratic fields rather than imaginary ones. So the first observation, which I've sort of made for you already, is that we only get primes in K. What's K? So in this tri-quadratic field, where it's defined, above Q's that are non-split for both of the discriminants and that divide such a positive integer. So that's the observations we just made. First observation. Okay, second observation. In this whole construction, there were 3 bits of input. There were 2 quadratic forms, and then there was also the choice of a prime p. We can also let that vary and wonder if I change my prime p, I get invariants associated to the same real quadratic points. but they might be different. So let me give you also a couple of examples. So let me compute theta p fg, where f is 1, 3, minus 1, so discriminant 13, and then g will be a couple of choices as I vary p that are admissible. So for instance, if g is something of discriminant 12, which is class number 2, we always get 2 invariants, and that's what the plus and the minus are. We recognize these algebraic numbers. When p is equal to 5, it lies in q adjoint the square root of minus 3. When p is equal to 7, it lies in q adjoint the square root of minus 1. So they lie in different fields, but they generate the same extension over the biquadratic real field. You see that the influence of p is, it's serious. If you change p, you change even the field of definition of the invariant. Okay, here's another example. When delta 2 is 45, we find the following numbers. And notice, by the way, as the prime gets smaller, the invariant gets richer somehow. That's another thing to kind of remember. And so here we see this number, it's in q adjoint the square root of minus 3. This one is in q adjoint the square root of minus 15. Still related sort of fields of definition and have the same compositum with the real biquadratic field. But now I'll invite you to look at the denominators of these expressions. So there's an observation 2 coming on the slide, but I'll give you a chance to observe it before I tell you what the observation is. Does anyone notice anything strange about the primes appearing in the denominators of these expressions? Particularly the exponents. It's hard to guess, maybe, huh? But look here, the denominator of this 5-adic invariant is 7. And the denominator of this 7-adic invariant is 5. Okay, that could be coincidence. So let's do the next one. The denominator of this 2-adic invariant has a 7 squared in it, and the denominator of the 7-adic invariant has a 2 squared in it. Okay, now it's becoming a little bit suspicious, maybe. Here's one more example to see whether our suspicions were correct. The 5-adic invariant has a 7 squared appearing, and the 7-adic invariant has a 5 squared appearing. Okay, now we're convinced we can make an observation, right? So observation 2 is that there appears to be a relation, in fact an exact equality in this particular sense, between the ord p of the q-adic invariant and the ord q of the p-adic invariant. At least on this limited data, but of course we computed many more examples. All right, so let me just tell you these kinds of numerical experiments, as we saw also appear in Gross and Zagier. There were many, many more, and we had the help of many people also to give them shape, especially the second one, which I'll get to in a second.
May I ask you just one?
Of course.
So are these numbers cohomological invariants? So if you change your
Yeah.
cycle by some coboundary,
Yes,
and
you,
evaluate,
yeah, then you get the same number.
you get the same.
Yes. If you change f and g in their SL2Z equivalence class, you also get the same number. So they're well-defined maps, really, from the product of the two class groups, which is a finite set, into CP, and they appear to be algebraic very often. No. Yeah, and it's also these kinds of invariances that, of course, give you confidence that it might be a meaningful invariant to define. Yeah, I should have maybe said that. Okay, so here's the first conjecture, and I'll make an assumption, which was always verified in any of the examples I gave you. P minus 1 divides 12. Disappointing, right? There's not so many primes. But okay, we have 5 primes. And after all, Gross and Zagier had 1 prime. They had infinity as their p-adic construction. They were doing an Archimedean construction. We're doing a p-adic construction. At least we could choose 5 different options. But I'll get back to that in a second. All right, so P is now 2, 3, 5, 7, or 13. This is the setup of what we obtain in general. K1 and K2 are 2 real quadratic fields associated to discriminants delta 1 and delta 2. They have a compositum L, which is a real biquadratic field, and they each have a narrow ring class field of that discriminant, delta 1 and delta 2. So I'll call that H1 and H2. And the Galois groups of these fields over K1 and K2 respectively are just the class groups, the narrow class groups of those discriminants. Right, so these Galois groups, they're also canonically split in this case, so I guess I didn't say that, but P is inert with respect to both of these discriminants. And then we get a canonical splitting by the Frobenius set P. Yeah? So they're generalized dihedral extensions. All right, so weak version of the Shimura reciprocity law that we conjecture in this case is that for any quadratic forms f and g in this notation that I forgot to define, so ignore that, we have theta p star fg, our invariant, which is a priori a local number, it's a p-adic number, is actually secretly global. And it should be inside of this field h1, h2. That's a little bit what the experiments have told us. Moreover, they should be permuted simply transitively by the action of this full Galois group h1, h2 over q. Meaning, if I act by any element in this Galois group, I get the invariant for some other f and some other g of that same discriminant. That's the shape of the reciprocity law. In fact, we can say, or we can conjecture even more precisely, which Galois conjugate gives us which other form. All right, so that's a little bit the behavior that we saw in these examples. All right, second of all, factorizations. We also looked at the factorizations of these numbers. I keep my assumption, p minus 1 divides 12. And now I have to tell you what these numbers were. These 13, 17, all these weird numbers we saw in the factorization. And we predict that these numbers can be computed as follows. Choose a pair of embeddings of the rings of integers of discriminant delta 1 and delta 2 respectively into a maximal order of the indefinite quaternion algebra over Q, which is ramified at P and Q. Okay, so it's a quaternion algebra over Q. In Gross and Zagier, you always had a quaternion algebra that was definite and ramified at infinity in Q. We've switched from infinity to P now, and so we're dealing with an indefinite quaternion algebra. Okay, if you choose a pair of such embeddings, then the conjugacy classes, these alpha I, they have a free action of the Galois group. That's a little bit what we saw already in the second lecture happening in the case of definite quaternion algebras. Up to conjugation by units, you get finitely many such classes of embeddings. And they're indexed, there's essentially twice the class number of many. That's this theorem of Doering, but in the indefinite sense. All right, so now there's an intersection number, int q alpha 1, alpha 2, entirely analogous to what we saw in Gross's response letter to Zagier. And it's an integer that depends on this pair of embeddings alpha 1, alpha 2, and it depends on this q, which of course is already in the quaternion algebra. And what it is for any pair of embeddings, alpha 1 and then a conjugate of alpha 2, I get two associated geodesics on the Shimura curve that's associated with BPQ. So BPQ, this indefinite quaternion algebra, has this maximal order R. I should have put that on the left maybe. But XPQ here is the quotient of H, the upper half plane, the usual one, which is why I put infinity to contrast it with P, modulo the norm 1 units in this maximal order. That's a compact curve. This XPQ, it's called the Shimura curve. It's defined over Q. And associated to my pair of embeddings, I get a pair of geodesics on that quotient. So what I do now is I take this pair of geodesics on the quotient and I intersect it in homology. Except I put a small Q weighting, which I'll just weasel in here, and I won't really explain what it is, which is for every intersection you get a pair of embeddings, and you measure also how congruent the images of O1 and O2 are modulo powers of Q, and that's what that MQ is. So there's a certain weighting that you have to put in to make it really exact. But the takeaway here is that these are topological intersection numbers. They're intersection numbers of pairs of geodesics on some other Shimura curve. Yeah. Okay, so what about these intersection numbers? Well, these topological invariants can be computed in a completely different way, and I should have put this on the slide actually, but James Rickards was developing these algorithms for computing very efficiently these intersection numbers, which is a completely different, has nothing to do with our computation at all. It's this intersections of geodesics on the Shimura curve. Nonetheless, there should be a connection, which was verified in hundreds of examples, thanks to James Rickards, and that's the second conjecture. If I take my invariant, theta p fg star, and I now believe conjecture 1, so it's an h1, h2, and I want to know what the ord q of it is for some German q in H1, H2 above Roman Q. Then the conjecture is that's equal to this intersection number of a pair of embeddings on this different indefinite quaternion algebra BPQ, on this completely other Shimura curve, which changes whenever you change its Q. So that's what the factorization conjecture is. Just like in Gross, he was sort of intersecting CM points on this zero-dimensional Shimura variety. Here, we're intersecting RM geodesics on a one-dimensional Shimura curve associated to this indefinite quaternion algebra. So that's the second conjecture, for which there is also lots of evidence. In particular, all of the more low-level observations that we did before, namely, they are always sort of non-split in the two, every Q that appears is non-split in the two, and they all must divide something of the form delta 1, delta 2 minus x squared over 4p, just like in, you might guess from Gross and Zagier. All of these follow from this more precise kind of conjecture. Okay? All right, so if you haven't followed any of this, here's the simple slogan. When p is one of these 5 primes, the invariant theta p star fg behaves in all key respects like the invariant, which I'll call theta infinity plus fg, which is the difference of the two singular moduli studied by Gross and Zagier. Okay? So if I suggestively introduce this notation for the difference of singular moduli, which we've been studying, where f and g now have negative discriminant, I'll call that theta infinity plus. I'm contrasting it here with theta p times. Infinity has changed to a finite prime p, and the additive construction here has changed to a multiplicative construction in the p-adic setup. Other than that, all of the statements are what you would get from the work of Gross and Zagier, formally switching infinity to p. Okay. Any questions?
That's a good question. So,
yeah.
In particular, you recovered the formula you wrote the first day that the norm of this number is the sum over all elements?
Well, so...
It's a pair, but if you consider all the pairs and you add over all of them, do you get the norm?
That's an interesting one. If I consider all the pairs, alpha 1, alpha 2, and I take the product of all of these invariants, like you would for the norm of singular moduli, I get 1.
Oh.
I get the number 1. And that's because complex conjugation here plays a very different role in the CM setup versus the RM setup. The Galois element that's complex conjugation, it's in the center of this dihedral extension. It's in the Galois group. And that changes the theory completely, and it predicts that, in fact, the invariants that we have, they need to lie in the minus part for complex conjugation. So if I take the norm all the way down to Q, I've lost everything. And that's reflected in the fact that all the polynomials that I showed you on the previous slides, they're all palindromes. I don't know if you noticed, but the coefficients are perfectly symmetric, which means that the norm of any of these numbers is always 1. So we don't want to take the norm to Q, which of course theoretically it's a major obstacle for proving anything. You have to refine then already that norm needs to be eliminated.
But you can take the norm to L, right?
You can take the norm to L, but that's similar, because complex conjugation, like I said, sits inside of the class group, so it'll also kill it. Yeah. Yes?
I'm a bit troubled by your class as opposed to
Ah,
to replace the star by a class.
yes.
Because this J of tau 1 and J of tau 2 is a kind of multiplicative portrait. It deserves to be viewed as a multiplicative, even though it does have this appearance of being additive.
Yes.
I think it should be viewed as a multiplicative.
Okay, yeah, that's fair. So Henri objects to the plus in the exponent with a very good argument. Of course, you can view it as a Borchards lift, so it has that multiplicative field. In fact, you can give an infinite product expansion for it as well, which is precisely the infinite product expansion that appears also in Gross and Zagier's paper, for instance. Yeah? All I'm trying to say here is that this invariant has the following very simple-minded additivity. So here we had an anti-symmetry in f and g in the multiplicative sense. Here we have an anti-symmetry in the additive sense. That's all I'm trying to say. So meaning if I switch f and g, I get minus the invariant. Whereas there, if I switch f and g, I get the minus in the exponent.
In fact, this one is actually symmetric.
If you take the absolute value, you mean.
We don't care about the minus.
Yeah.
But it's actually symmetric, and it's weird to have it with H0 instead of H1. And
But what,
on H0, and modular forms are a ring, of course, and you
Yeah.
can add and multiply.
Yeah.
But we're generalizing the multiplicative aspect.
So, but what's the symmetry you say here? I mean,
this minus sign is almost a distraction. The fact that
Yeah.
now and check that,
I agree. I'm not trying to say anything
multiplicatively,
too
it's
profound
harder
here.
to avoid ignoring it.
Yeah, absolutely, absolutely. So maybe don't make too much of the exponent, the times and the plus. The point I was trying to make was very simple-minded, just that the antisymmetry here is an additive one instead of a multiplicative one. But actually, you make a very good point. Maybe this is... So forget about the plus. Focus on the infinity and the p.
Yeah, the analogy is even strong. It's really key and infinity.
Exactly, that's really the main thing that I want to say, yeah, absolutely. Yeah. Yes?
So in Gross and Zagier, this is like P1, J, F, J, G. So this is like in the modular environment, the modular polynomial, and it was 1. And Gross and Zagier
yes.
also have a evaluation or polynomial. So
Yeah.
do you have an analog for
Of the higher modular polynomials. Yeah, you can apply Hecker operators also to this theta p. So these theta p's, they live in these cohomology groups, so naturally inherit a Hecker action. And you can apply the nth Hecker operator to this theta cocycle, and then evaluate the g. And that should be the stand-in for these higher modular polynomials that we get. Now what's funny is that the Hecker theory on this space of rigid meromorphic cocycles, it's very mysteriously behaved. In fact, it doesn't have any stable subspaces, except the analytic ones. So the space of analytic cocycles, which don't have any poles at all, that's a finite dimensional subspace, as I mentioned before, which is roughly isomorphic to the space of weight 2 modular forms on gamma 0 of p, and that's the only stable subspace. So anything truly meromorphic that you throw in will never be a Hecker eigenform. So it'll always be, the poles will sort of proliferate.
But so for these primes,
Yeah.
that space doesn't exist, right?
Exactly.
And you don't have modular form
That's
of
exactly
gamma
right.
0 p.
That's exactly right.
But so how they interfere with these with such formulas? You think if p is not in this small
It's an excellent question. So what is the meaning of the invariant if p is not one of these 5 primes? Yeah. Can you maybe ask me again at the end of the lecture? Because I would like to get to the Kudla program because I promised Fabrizio. All right, so this is the stage where we're at. We define these crazy invariants and they appear very nice and have interesting properties, except it's quite difficult to prove any of these conjectures. So I would like to offer a couple of sort of data points where something like a p-adic Kudla program actually offers a bit of clarity, at least on some of the conjectures. And I'll focus on a degenerate case, which is joint work really with Darmon and Alice. And it's perfect actually that Alice gave her lecture this morning because I will talk very much on the same thing, except maybe with a few more variables. Well, with one more variable than what happened today. So it'll be very recognizable, hopefully, compared to what we saw this morning. All right, so I'll offer 2 attempts and I'll focus mostly on the first one, which is in the theme of this morning's lecture. How can we try and prove anything? So let's take a specific simple case, and the case that I want to look at essentially is the invariance of the cocycle that I get from a quadratic form of discriminant 1. Yeah? The smallest discriminant I could have taken. That's positive. And we get sort of a degenerate case, and in that case, the algebraic numbers that come out are precisely the Gross-Stark units that we saw appear this morning. So that's a little bit the story that I want to tell you about today, and in that case, we can prove that this is the case using ideas very similar to those appearing in the work of Gross and Zagier, which might be construed as an instance of a p-adic Kudla program. So just to remind you of the setup, which you already saw this morning, so Alice explained much better than I will the setup, and so the setup here, so things will not be over Q, they'll be over a real quadratic field, but other than that, everything is more or less identical to the situation we saw this morning. So just a brief recap. So I'll take a positive discriminant delta. I'll take it to be non-square now. And F will be the real quadratic field associated to it. H will, what you would guess, be the ring class field of discriminant delta, whose Galois group over F is still the narrow class group of discriminant delta. Yeah? So same situation as before. And now I will allow myself to choose a non-trivial character of this extension H over F. Actually, I want this character to be odd. I hope I say that later in the slide. So this is the diagram of field extensions we have. All right, so now S will be a finite set of places in my real quadratic field F, including all the Archimedean ones. So the setup is very similar to that of Stark's conjecture. And just like we saw this morning, we can define two q-bar vector spaces. The first I'll call U, and it's a group of S units inside of this field H, tensor q-bar. And we know by the Dirichlet unit theorem, as a Galois module over G, this decomposes as follows. So it's just a direct sum of inductions from any of the stabilizers above a fixed prime V in S, all the way up to G, of the trivial representation. And if you put them all together, you have the trivial representation once extra, so you subtract it again. That's what that last line is. Okay, so U chi will be the chi isotypic component of this unit group U. So it's a finite dimensional q-bar vector space with an action of G, which we fully understand. And I'll take this U chi. And Dirichley's unit theorem then allows you to work out that the dimension of this unit group, so this chi isotypic part, is precisely the number of places in S, so that chi of V is equal to 1. No? So the number of places that split completely there. All right, so I will put myself in a very special situation, and the situation will be that of a real quadratic field. So I have my two infinite places, infinity 1 and infinity 2. And I have a place P, where P is a prime in Q, really, that's inert in F. Yeah, so there's really only one prime above it inside of F, and I put that in my set S. Yeah, and the character chi, luckily, I remember to say, is totally odd. That's the situation I want to put myself in. Okay, so in this case, this dimension formula gives me that it's a one-dimensional space, and it's spanned precisely by this Gross Stark unit U chi, which we saw already defined this morning. So this U chi, it's an algebraic number in H, and it's a P unit. Okay? So it's well defined up to rescaling, but then this OR P condition rigidifies it. Okay. Now, what do we do? Essentially, we study now the situation precisely as we did this morning. But instead of the Eisenstein series over Q associated to a character, I'll now give myself an Eisenstein series over F, this real quadratic field, associated to the pair of characters 1 and chi, just as we did this morning. So it's of weight 1, 1, and it's associated to the pair 1 and chi. And just as Alicia did this morning, you can switch 1 and chi to a chi and 1, but that gives you the same form in weight 1, 1. But they're part of two different Eisenstein families, exactly like we saw this morning. Now, what we can ask is we can study what are all the ways that you can p-adically deform in the sense of eigenvarieties. And we saw the one variable case appear this morning where we had an eigencurve. Since we're over a real quadratic field here, we have an additional variable, and it's really an eigenvariety. And up to Tate twists, it has dimension 2. Now, the eigenvariety around E has actually been described completely by Bettina, Dimitrov, and Shi. So they describe what the geometry looks like, and it looks a little bit like this. So the picture is that we have an eigenvariety up there, which is now, it's like the eigencurve we saw this morning, but it has extra dimension, and it lives over weight space. And this weight space I'll put below. And so there's a map here from the eigenvariety to weight space. And the geometry, formally in a neighborhood around this point defined by the form E, looks as follows. So it has this sort of étale part over weight space, which is the cuspidal part. That's the two-dimensional thing in this picture. It's this two-dimensional cuspidal sheet. And then you have these two strands. One I've colored orange, and the other I forgot to color orange. But they're the two Eisenstein families that we saw also appear this morning. But besides the two Eisenstein families, which live entirely in parallel weight, there is also this étale cuspidal family that passes through this point. So it's exactly the situation we saw this morning, where there's really three families going through this one common specialization. It's just that the cuspidal one has more dimension than it did this morning. But the situation is exactly the same. Okay? All right, so I will now focus on two specific families that I can take. So I can put myself in the position of this E11, this weight 1 Eisenstein series, and then choose two different ways of deforming it. One is the orange one. That's the explicit one. That's the Eisenstein family. So this parallel weight 1 plus S, 1 plus S family, where S is the variable here that indexes the weight, is completely explicit. Yeah, here it is. The formula doesn't really matter, but its Fourier expansion can just be written down. Just as in the beginning of the work of Gross and Zagier, the Fourier expansion of this real analytic Eisenstein series was sort of the starting point of their calculations. What we want to do is we want to also consider a cuspidal family passing through this point, but we want to do something in the style of the Kudla program. We want to know explicitly what arithmetic information is in the Fourier coefficients of this family. The only problem is there's no explicit formula for it, so we have to already work to figure out what the Fourier expansion looks like of this green anti-parallel weight 1 plus s, 1 minus s family. So it's not explicit, but we can make it explicit using exactly the techniques that Alice introduced this morning. Because what we can do is we can put ourselves on the Galois side and we can calculate the Fourier coefficients of this mystery green family by instead calculating all of the modular Galois deformations of this reducible Galois representation, which is just the sum of the characters 1 and chi, which you could say is associated to this Eisenstein series. So it's a Galois representation of the absolute Galois group of F, valued in GL2 QP bar. Okay? Now, of course, there's technical complications. It's a reducible Galois representation, so you have to rigidify or take a non-trivial extension, exactly like was discussed also this morning, but I won't go into these kinds of more technical issues. What I want to show you is, exactly like this morning, the calculation of all of the deformations of this Galois representation. Algebraically, it takes place by computing what the H1 of the adjoint looks like. And the key is that the adjoint of this representation is just a sum of 2 characters. The adjoint is just a sum of 4 characters. It's 1 plus chi inverse. So it's a very simple representation, and H1 of the adjoint, therefore, naturally splits up as H1 of characters. And just like we saw this morning, this H1 of characters, by global class field theory, gives us access precisely to the Gross-Stark units by evaluating at Frobenius elements. So by global class field theory, the classes that index this deformation, they live in H1 GF chi, which by inflation restriction is this home of this GH, the field that trivializes the action of chi isotypic component. And then you can make that explicit exactly like this morning to get this home set of the set of units tensor ZP into QP bar. Yeah? All right, once you evaluate that on a Frobenius element to compute Frobenius traces, precisely like this morning, the Gross-Stark units U chi finally appear. Yeah? So hopefully this is recognizable from what Alice explained. This is the mechanism where the algebraic numbers come from. All right, so what do we do with this? How do we put these together? Well, we take this strange combination of this explicit parallel weight deformation and then this more mysterious anti-parallel weight family. And there's sort of a wisely chosen non-trivial combination of these families, which we take just because the algebra compels us to take that particular combination. And we then subject it to the following 3 operations. So the first is we restrict it to the diagonal, just like happened in Gross and Zagier. We take the first order derivative, like happened also this morning, and then we take the ordinary projection of the result. So the same 3 operations that we saw in Gross and Zagier with the holomorphic projection replaced by the ordinary projection. All right, so we worked hard for our Fourier coefficients of the green guy, the Fourier coefficients of the orange guy we got for free, and now we can calculate what the Fourier coefficients of the end result of this calculation is. And what we get is the following. So we get a modular form whose Fourier expansion is now an instance of the invariants that we define, these RM invariants, but it's a degenerate instance. So the constant term is the logarithm of U chi, this Gross-Stark unit. The higher Fourier coefficients are the evaluations of this theta G star, my co-cycles associated to a form G, where G is the most degenerate case you could have taken. It's this quadratic form, 0, 1, 0 of discriminant 1. We call this the winding co-cycle in that paper. All right, so we get this generating series with these kind of explicit infinite products that we defined before as the higher Fourier coefficients, and this more subtle algebraic invariant as the constant coefficient. But because it comes through this whole meat grinder of these three operations, we know that the end result is actually a weight 2 modular form on gamma 0 of p. Okay? All right, so we have a sort of a modularity result for the RM invariance that we defined before, coming from a very p-adic construction, considering p-adic deformations of Eisenstein series, which is the kind of thing you might see in a classical Archimedean Kudla program. Okay, so let's just finish off that story. What do we do with this generating series? Well, it's already in this small finite dimensional space. If P is a genus 0 prime, that only contains the Eisenstein series. In general, it contains more things, but we can always project to the weight 2 Eisenstein series. And that's the same as projecting the cocycle theta G star to the unique Eisenstein class in these cocycles for the group gamma valued in analytic functions modulo scalars. So these things don't have poles, and like I said before, when they don't have poles, this H1 is actually a nice finite dimensional space, which is more or less just H1 gamma 0 of P with coefficients in Z. So classical space of modular forms. So if P is a genus 0 prime, if you were happy with that, you don't have to do this. Otherwise, you project to the Eisenstein part, and you get the main theorem of that paper, the second paper we wrote with Darmon and Pozzi, which shows that this Eisenstein class, which is often called the Dedekind-Rademacher class, evaluated at chi, is this chi Gross-Stark unit. And you should view this as an analytic expression for the Gross-Stark unit. It's sort of something that comes about by explicit infinite products and produces the Gross-Stark unit at the end of it. Okay? All right, so in this case, the RM invariance that we get for this very specific, most degenerate class is actually provable. So the fact that it's algebraic is provable. We know exactly where it lies. We know it's prime factorization, but it's not very rich because it's a p unit. And just a couple of comments on that. This Eisenstein class lends itself excellently to generalization. And so there's a beautiful recent paper for Rosette and Chu, where they generalize the construction of this Dedekind-Rademacher cocycle to SLNZ, where you can also hope to get invariance over bigger totally real fields than just real quadratic fields. There might also be mention of this next week, which is, I don't know, but I'm guessing it might be mentioned.
Is it SLNZ or SLNZ?
It's SLNZ. Yeah. Conjecturally, it should extend to SLNZ 1 over p. Well, actually, maybe Marty is here. I should rephrase this question to him. But is that fair to say?
Hopefully soon.
Okay. Hopefully soon. All right, the second thing I want to mention is that everything here is so explicit. I said you should view this as an explicit analytic expression for the Gross-Stark unit. And in fact, that message was sort of taken to its logical conclusion by Dam Johnson, who really made the proof, this analytic sort of Gross-Zagier style p-adic Kudla proof, into an algorithm for these Gross-Stark units. And so here's just an example. So let's take this real quadratic field, 136. That's class number 4. So the Gross-Stark unit will live in this kind of big dihedral extension of degree 8 over Q. And you can choose the prime p is 19, because why not? It's big, and so I can show off some of his timings. What the algorithm is, it computes all of the higher Fourier coefficients using the explicit nature of these cocycles, uses the fact that this is a form in M2 gamma 0 of p, and then solves for the constant, because there's only one Eisenstein series in there. And so in less than 3 seconds, you get a polynomial that you recognize from this, which is this beautiful polynomial, and 361, of course, is 19 squared, as it should be. So you can read more about that in the corresponding papers. Okay, I am, in spite of what I had intended, running very low on time, but I still want to give you a very quick impression. If we're dreaming of having a p-adic Kudla program, it was nice in this case of the RM invariance. You see, for me, I take this very simple-minded viewpoint on the Kudla program, whereby maybe generating series coming from algebraic cycles can be shown to be modular. Let me take that, and forgive me for this very lowbrow interpretation of the Kudla program. But what's missing here in these RM elliptic units is that we don't really have algebraic cycles. That's kind of the missing part. And that's why we imitate more the analytic proof that appeared in Gross and Zagier to avoid having to use CM theory. There's no substitute for these CM elliptic curves that appear in this work and the intersection numbers that we computed before. But what you could do is, now that we have this sort of analytic arguments in the RM setup and the geometry is absent or mysterious, we can now transpose it and try and go to a situation where we can maybe run a similar argument, but we do have algebraic cycles. So we can sort of get a better feeling for what the meaning is of all of these weird series that we're producing here in a situation where there is geometry. So I just want to say very quickly that this is exactly what happened in the following work. So what you could do is you could choose, again, the Shimura curve associated to an indefinite quaternion algebra Bn, where n is p times q. Still a very global object. And you can again suppose that xn has genus 0. Yeah? So that means that there is some isomorphism with the Shimura curve and p1. And I'll choose one. I don't really have a canonical one, but I'll call it Jn. Okay. Now, Darmon and Giampietro, they made a systematic computational study of the values, which are the cross ratios of this J function, at a pair of CM points P1 and P2, and then a certain conjugate P1 prime and P2 prime. Okay? Now, why this cross ratio? Well, because Jn is not really well defined, but the cross ratio is. That's independent of the choice of this isomorphism that I make. So I get a well-defined sort of CM invariant in this setup, and because because I don't have cusps, I don't really have a canonical choice of such a Jn. Okay, so here's an example. So they conjecture an explicit formula, which it doesn't really matter too much for my talk today, which should be over already, for the value. And so I'll just give you one example. So if you take P1, P2 of these discriminants, minus 43 and minus 163, which appeared on the very first slide in the letter of Zagier, but now on this Shimura curve, where n is equal to 6, you get the following cross ratio. So again, a very nice explicit factorization for which Darmon and Giampietro conjecture an explicit formula. Now this formula, you can now ask yourself, can we prove this explicit formula in the style of Gross and Zagier? And we had two proofs. We had an algebraic proof and we had an analytic proof. The algebraic proof was worked out by Phillips in his 2015 thesis. And what he does is he does exactly these kinds of methods, but it's more complicated. So this Xn is still a moduli space. It's a moduli stack for abelian surfaces which have quaternionic multiplication. And so they have these special cycles also, these CM points, which have, besides their quaternionic multiplication, also a CM action. And what Phillips does is he computes exactly the arithmetic intersection numbers of these CM divisors on this curve. Okay, so if you have that, you can use these intersection numbers and give a completely algebraic proof of this formula of Darmon and Giampietro. So this fits sort of squarely in the classical Kudla program maybe setup of what you would do when you did have algebraic cycles. But what we can do now is we can pretend that we don't know that. And we can pretend to lift off sort of a p-adic analytic proof that doesn't depend at all on CM theory to try and obtain the same result to fill that missing gap of what might be the crucial ingredient for the p-adic Kudla program approach to this kind of question. And that's exactly what was done by Das, who will also be here next week, and I think he will maybe speak about this. And what he does is he considers exactly this setup. Yeah? So he takes K1, K2, just like in Gross and Zagier, two imaginary quadratic fields. Chi is the genus character of the real quadratic field inside of it. And you take the Eisenstein series with this representation, 1 plus chi, where chi is now this genus character. It's the same Eisenstein series of Gross and Zagier, literally. It's exactly the same Eisenstein series. It's just a different way of deforming it. They deform it in a real analytic way. Das deforms it in a p-adic way. Now the form is trivial, yeah, so the Fourier coefficients all vanish. But nonetheless, you can take the Galois representation and get an idea for all of its deformations. And Das considers a p-adic deformation in the anti-parallel weight direction, very similar to all of the things we just did in the RM setup. And then subjects it to the same operations, diagonal restriction, derivative in S, and ordinary projection. And at the end of the day, exactly by analogy with the proof of Gross and Zagier, he obtains that the norm of these cross ratios is some explicit formula. Same kind of formula that we saw in Gross and Zagier. The meaning of the symbols on the right is not so important for today. So you can lift off precisely this same proof where you've never used any algebraicity of these values of the J function at all. You haven't used CM theory at all. Okay, and just to finish, I just want to mention two things. So one is you can now go double back and you can consider the same setup and try and do now an Archimedean proof of that same situation. And that's precisely what Krabit-Nicolaou does in his theorem, a purely Archimedean proof of that same theorem, which he did in a master thesis. Finally, I would like to mention that since we're talking about the Kudla program, and I'm giving you this very childish viewpoint on the Kudla program, I should mention that it's also possible to rephrase many of these things from the point of view of Ben's lectures. And so there's exactly this same setup has appeared also in a recent work of Benich, Darmon, German, and Rosette, who show that the following generating series is modular. And so I don't explain what the symbols are, but it's precisely what you get from Ben's point of view if you take this indefinite quaternion algebra and you take the trace 0 elements inside of there. That's a rank 3 Q vector space which has a quadratic form. It's signature 1, 2. And if you go through the definitions that he gave us, you get precisely that if you take the symmetric domain D of things with norm 0 and you quotient out by the orthogonal group, you get precisely xn. You get precisely this variety. And the special cycles that he defined, these Z deltas, are precisely these CM divisors on these quaternionic Shimura curves. And if you make their generating series, where L, as before, is the tautological bundle on this space, then this series is modular and it's valued in the Picard group of xn tensor with Q, which is a classical result that was really proved by Gross, and Zagier already. There's nothing p-adic about this statement. But what's interesting about this new proof in this last paper, which is sort of on the other side, it's a flip side of the coin of the analytic proof of Das that I just discussed, is that also it produces this series in a p-adic way. Das' result was integral weight, so he started with weight 1, 1, and he deformed this weight 1, 1 form after restriction to the diagonal. Here, the form is on the half integral weight side, so it's of weight 3 halves, but the way that this generating series is made, or rather its linearizations along the tangent space, is precisely by taking a modular form of weight 3 halves and deforming it in a p-adic family. And it's a p-adic family that also vanishes at weight 3 halves, and that its first order derivative projected via the ordinary projection gives you precisely this series. So it's clear by now that there's many data points, and I just tried to give you a couple, that suggest that there is really, these two worlds are talking to each other in an interesting way. And it's interesting to explore both setups where there is no geometry and where you have to rely on some p-adic Kudla program in order to even prove the algebraicity of your results, but then to also revisit these settings where the classical techniques do apply to get a better feeling for the geometric interpretation of some of these analytic objects that show up there. So that's really the end of my lecture. I hope that it gives you some data points to consider when you decide, because I haven't decided and I certainly don't know what the p-adic Kudla program should be, but you will decide, and maybe these will be interesting data points for you to take into consideration when you outline the confines of this kind of purported p-adic Kudla program. And with that, I'll stop, and I'm very sorry for going over time.